Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2011, problem number 2. Let G be the following set. It consists of matrices, 2 by 2 matrices, with first column A0, second column B1, where A and B are elements of Z7 and A is not 0. We wish to prove two things. First, we wish to prove that G is a multiplicative group, so it forms a group with normal multiplication of matrices. And part B, the interesting part, the set of homomorphisms from our group G into Z7 with addition, we are considering Z7 with addition. This set is trivial, so the only homomorphism from G into Z7 is the zero homomorphism. It's a very nice problem. Here are my hints. Wrong, sorry. Oh, here it is. First hint. Z7 is a field, which means that for every element of Z7 which is not 0, it has an inverse. So A times A inverse is 1. For part B, suppose that we have some homomorphism of groups and use this well-known fact that kernel is a subgroup of our group G, and the cardinality of every subgroup of some group divides the cardinality of G itself. We wish to show that the kernel actually equals G, and it suffices to show that the cardinality of kernel is greater than cardinality of G over 2. Because the only possibility given this divisibility is that cardinality of kernel equals the cardinality of G. And crucial observation, you should justify that AB01 raised to the 6th power is always identity if A is not equal 1. So give this problem a try. Right, so let's tackle part A first. Let's do part A. First, we wish to show that our operation is that if we multiply two matrices from G, we get again a matrix from G. So let A, B, C, and D be from Z7, and moreover, I will assume that A and C are not 0. Then notice the following: AB 0, 1, CD 0, 1. After multiplication, we will have AC 1, AD plus B 1. And also here is 0, not 1. Clearly, again, this is in our set G, because if we multiply two non-zero elements of a field, this is again not 0. So this is again in G. What else we wish to show? Well, obviously, the identity matrix is in G. It's obvious that it is. Alright, and the last thing, we wish to show that there is actually inverse of every matrix. And this part right here is very telling about what the inverse of a matrix should be. Notice that if I multiply AB 0, 1, I wish to multiply by something. I wish to multiply by something and get 1, 0, 0, 1. Well, to get 1 right here, I should define C to be A inverse. And to get 0 here, I should define D to be A inverse times B, and also minus. And after doing that, let's notice we have A inverse, 0, 1, and here we have minus A inverse B plus B. it's the identity matrix, as it should be. And what about multiplying the other way around? Well, obviously we will get identity, but let's convince ourselves. It's A inverse times A, 0. Then we have, here we have 1, and here we have A inverse B minus A inverse B. Again, the identity matrix. Which means that our structure is a group. So G with matrix multiplication is a group. Alright. Now, part B, much more interesting. So now suppose now that we have some homomorphism of groups. So it takes group G and maps it into Z7. And again, here we consider multiplication, and here we are considering addition. Suppose now that this is a group homomorphism. Alright. First, what's the cardinality of G? Well, the cardinality of G, if you think about it, we have two parameters, A and B. A can be from 1 to 6, B can be from 0 to 6. So cardinality of our group is 42. Alright. Now, let's take any matrix whatsoever, A, B, 0, 1, and I wish to raise it to the 6th power. You will see in a moment why. So first, let's compute its square. Computing square, it's A squared, 0, 1, and here we have AB plus B, or A plus 1B. Let's write it in this way, A plus 1B. I wish also to compute its cube. Well, to compute its cube, I will take AB01 and I will multiply it by square, which I have right here. A squared, A plus 1, B0, 1. And what is that? Well, it's A cubed, 0, 1, and in the last place we'll have A times that, so it's A squared plus A plus 1 times B. Alright, and now we can compute 6th power, AB01 to the 6th power, by raising this matrix to the 2nd power. And to compute square, we can use the formula derived for the first part. So it's A cubed squared, so it's A to the 6th power, 0, 1, and here we'll have A cubed plus 1 times A squared plus A plus 1 times B. Verify it yourself if you are not believing, but you should. Alright, and now I claim that if I take my claim that if A is Z7 but not 0, not 1, and B is any element of Z7, then I claim that A, B, 0, 1 to the 6th power is the identity matrix. How to prove my claim? Proof. I will just consider A case by case. Case by case. Let's see. What happens when A equals 2? First of all, maybe let's notice that A to the 6th power is always 1 because of Fermat's little theorem. So maybe let's write it. A to the 6th power equals 1 by Fermat's little theorem. because we are taking congruence modulo 7. But what about this term? It should be always 0, yes? How to prove it? Well, I will proceed case by case. First case, when a equals, let's say 2, then notice that then a squared plus a plus 1, it's 4 plus 2 plus 1, it's 7, but 7 is 0. So we have this term is 0 as it should. What then? A equals 3. Notice that if a equals 3, then a cubed plus 1, it's 27 plus 1, it's 28, but 28 is 0. So again, what I will copy it, because or maybe, you know what, I will write in. Next case is what? A equals 1 is not. A equals minus 1, also known as 6. Then a cubed plus 1 is 0. What else is left? What about minus 2? Well, then a cubed plus 1, it's minus 8 plus 1, it's minus 7, minus 7 is 0. And one last case, a equals minus 3. What then? Then a squared plus a plus 1, it's 9 plus 1, so it's 10, 10 minus 3, 10 minus 3 is 7, 7 is congruent to 0. So in every case, each time this term of our matrix is 0, which completes our proof. Proof of our lemma, yes? Proof of our lemma. Right. And now, let's notice the following. That h, so suppose that a is not equal 1. Notice that then I can take h of my matrix AB 0, 1 raised to the 6th power, and I can write it in two different ways. On the one hand, it's just h of the identity matrix, and since this is the identity of our group, it should go to the identity of group Z7, which is 0. But since this is homomorphism, it's 6 times h of AB 0, 1. Yes, because our function is homomorphism. But notice that this means that 6 times something equals 0. 6 is invertible in our ring Z7, which means that h of a, b, 0, 1 equals 0, which means that i.e. a, b, 0, 1, every element of this form is in our kernel, our function. But how many matrices of this form are there? Well, it's a new page. How many? Let's count. A can be chosen in 5 ways. B can be chosen in 7 ways, which means that the cardinality of our kernel is greater than or equal 5 times 7, which is already 35, which is greater than cardinality of our group divided by 2, which means that our kernel must be the entire group G. And that means, i.e., our homomorphism must be constantly 0. And this closes our proof. The only homomorphism of these groups is the zero homomorphism. Thank you very much for watching. I hope that you've learned something new this time. It was a very nice problem. I wish you a nice day, and I will see you next time. Goodbye.